Hi everyone. In this video I just want to take the time to go through the last couple of examples of Chapter 11. Chapter 11 is on subgroups, and this week the assignment is covering this material, so it's also on subgroups. And I didn't get to the last example, and I think it would be good to at least have this done so that you can work on a couple of problems that are related to it on the homework assignment. So for example, on our homework assignment we've got a question such as question 4, determine which elements in Z22 are generators for Z22. Also list the elements of order 6 in Z600. Find the subgroups, so question 6, find the subgroups and determine generators for the subgroups for Z12 and Z17. So these three questions are all going to be related to this last example which we didn't get to. So it's worth going through this example, and I didn't want to have to wait till Friday to do it. So let's get to it. So just a reminder, today in class we covered these main results for subgroups. Lagrange's theorem says that if you've got a finite group and H is a subgroup of it, then the size of H has to divide the size of G. So that's a very nice condition we have on subgroups. It tells us that the order of a subgroup, or the cardinality of the subgroup, or the size of the subgroup, we'll use all those terms synonymously, has to divide the order of the group that it sits inside. And then as a consequence, corollary 11.4.2 says that the order of an element has to divide the order of a group. So those are two different uses of the word order. One is order the element, smallest power that will kill it, that'll turn it into the identity. And that order has to divide the order of the group, so the size of the group that it sits inside. So those are two important results that we have. Why are they important? They're important because they impose a lot of structure on the objects that we're dealing with. And that's what we're going to exploit in this section. So I'm calling it Cyclic Groups Revisited because we introduced cyclic groups in Chapter 10, and now we're revisiting them with these new results about order and Lagrange's theorem in mind. Okay, so the first few comments we're going to make are about general cyclic groups, and then we're going to focus on the group of integers mod n and see what they tell us in those instances. So for example, in a general cyclic group, well, as is written here, the fundamental theorem of cyclic groups. So what we have in a general cyclic group, so remember, a cyclic group is a group for which every element can be written as a power of a single element called the generator. So if we have a cyclic group, so a group G, and it can be generated by a single element, so all powers of that G are going to create or generate all the elements of our group. Then what we have is that any subgroup of this group must also be cyclic. And so that's a nice result because that tells us that there's not some sort of chaos that kind of happens. There's not anarchy. There's this groups and their subgroups obey certain structures. Okay, so what else do we get about this? So every subgroup of a cyclic group is cyclic. That's the first sentence. Moreover, if this group G has order n, then in other words, the little g has order n as an element of the group, then for each divisor of our set, the cardinality of our set, or for each divisor of the order of our group G, there is exactly one subgroup of that order. We're going to get lots of practice with this, lots of examples with this to make sense of it, but basically it says there's divisibility structure at play here. That if this group G at the very top, let's say it's order 10. Suppose that this little g generates a group of size 10. Then what that tells me is that there's got to be a subgroup of size 5 because 5 divides 10. There's got to be a subgroup of size 2 because 2 divides 10. There can't be a subgroup of size 7 because Lagrange's theorem tells me that a subgroup has to have, the size of a subgroup has to divide the size of the group. And if this group is size 10, it can't have a subgroup of size 7. So Lagrange's theorem is a result that tells us that if for our big group G, we have a subgroup, then the size of the subgroup has to divide the size of G. But it's not necessarily the case that if I have a group, then for any divisor of that size, there is a subgroup of that order. Whereas we have that for cyclic groups. Any divisor of the size of the group, there's a subgroup precisely of that order. So this is what we're going to play with now. We're going to play with just cyclic groups. So our first example, consider the subgroup of permutations on 5 objects, which is generated by this one element. This one element is what we're going to call G. So there's G. Notice that G has order 6. As an element, as a permutation, its order is 6. It's the least common multiple of 3 and 2, the cycle lengths. What does that mean? That means that the group it generates has 6 elements. So the group it generates has order 6 as well. Those are 2 different uses of the word order. The first one is order as an element. The second one is order as a group, size of the group. So this has order 6. It's a cyclic group of order 6. Now, what I'm interested in is knowing what the orders are of all of the other elements in this group. So let's just list them out. We've got G, which is G1. We also have G squared, G cubed. We've got G to the 4th, and we've got G to the 5th. And then G to the 6th is the identity, and I don't need to list that one out because the identity has order 1. So what are the orders of each of these elements? Well, this one we already listed. It's order 6. What about G squared? Well, what we could do is we could square it. There's a permutation there. We could just square it. See that the one cycle gets killed and we're left with this 3 cycle 1, 3, 2. So we could square it to read off the order. But I want to encourage you to think more in terms of higher order thinking, not so much in terms of computation. The more we can think sort of logically about these things without having to do computations, the better off we're going to be in being able to quickly conclude results. So here we've got G squared, and I want to know what is the smallest power that kills it. So what is the order of this element? Well, if I take G squared, I want to raise it to a power, the smallest number possible, to get the identity. I already know the smallest power of G that will turn it into the identity is 6. So if I squared G squared, that would only get me G to the power 4. That wouldn't be the identity, because if it was, then little g would have order 4 and not 6. So I can see that I'd have to cube it to get to the identity. So that means this has order 3. Now we could see that immediately. It's a 3 cycle. Yeah, it has order 3. But notice my deduction of the order was not to do with the fact that it was a 3 cycle. I deduced what the order was just because G had order 6, and therefore its square has to have order 3. We can do the same thing for this one as well. This has to have order 2, because in some sense that power 3 is already killing a lot of G. And I just have to figure out how to finish off the rest of it, and that is squaring it. And that'll make it a G to the 6, which is the identity. So that has order 2. We could also see that, I'll write it in purple here, we could also see that as, well, that's really just the 2 cycle 4, 5. So yeah, clearly it has order 2. But we can conclude it has got order 2 without having to refer to its cycle structure. How about G to the 4th? Well, again, I want to try to figure out what power can I raise G to the 4th to in order to kill it. Well, I've already got it raised to the power 4, which means I've already got a 2 in the power already. I know 6 kills it. So I can use one of the 2's in the 4 and say, well, it's already partially killed. If I raise the rest of it to the power of 3, then that'll kill it completely, because now that's G to the 12. G to the 12, that's G6 squared. G to the 6 is the identity, so this is the identity. And 3 is the smallest number that does this. So this has order 3. How about G to the 5? Well, again, we can think, what number do I have to raise it to in order to get the identity? What number do I have to raise it to get the identity? Well, if I squared it, I get G to the 10, which is essentially G to the 4th. It's not going to be the identity. I could cube it. I get G to the 15. But every time I get a G to the 6, it becomes the identity. So G to the 15 is equivalent to g cubed, still not the identity. In some sense, I'm starting to do modular arithmetic here. I'm trying to raise it to a power and see when is that power divisible by 6. So what is the smallest power I could put here? Well, I need 5 times whatever I put there to be divisible by 6. And since 5 shares no common divisors with 6, I'd have to use the full value of 6 up there to get the identity. And so that says this is order 6. Now we think about how that worked. All the way along I was trying to use some of the existing power. If it had a common factor with 6, then I'm saying, oh, it's already partially killed. I just need to finish it off with another number. But g to the 5 didn't have any common factors with 6. So in order to kill it, I still had to use the full value of 6. And that tells me then something interesting. Well, sort of noted in the next result, but I'll just summarize what we found here, is that this group generated by g, well, g to the 5 also has order 6. So that group is also generated by g to the 5. So every permutation in this group, every product of or power of g, could be written as g or g squared or g cubed, or it can be written as g to the 5 or g to the 5 squared or g to the 5 cubed. So we can either use g or g to the 5 to generate the elements of this group. What is g to the 5 in this case? Well, this would be the first 3 cycle raised to the 5th power, which would be its squared. I'll write this in purple. So it's 1, 3, 2, and it would be the 2 cycle raised to the power of 5. So that's what the cycle structure would be. Yeah, it's of order 6. It's really just the inverse of g in this case. So it's rather obvious in that sense that if every element of this group is some power of g, then every element is also a power of its inverse. Okay, so what do we get now? Well, this example can sort of be carried forward in the sense that if we have a cyclic group, g is generated by little g, and let's say it's order n, what are the other generators of the group? What are the other elements whose order is the full size of the group? Well, those are precisely the powers of our generator where the power is relatively prime to n. In other words, they're the powers, g to the k, where k has not killed any of g. The only time it would have killed a part of g is if k shared a common factor with n. So this is precisely g to all the relatively prime numbers to n, and those are the other generators. How many other generators are there? Well, there are all the values of k, which are relatively prime to n, and we introduced a function back in our number theory appendix that counts these things. That's Euler's phi function, phi of n. Phi of n is precisely the number of integers between 1 and n that are relatively prime to n. And so what this tells us is that if I have a cyclic group of size n, then there are phi of n different generators that I could use to generate the elements of that group. One of them is g, little g in this case. All the other ones are various powers of it where the number is relatively prime to n. Let's go back. I think we had an example earlier on. I might have been on, yeah, it was in the previous lecture. So I'll scroll back to just save our spot here. That's where we were. I'm going to go back to the previous lecture on groups. And here we are with our example of additive group of integers, mod 5. And what we did in this case, we worked out the Cayley table for it. But we can go a little bit further now. We can say this group is cyclic. Every element is generated or can be obtained by taking 1 and adding it to itself a bunch of times. So I can get 3 by taking 1 plus 1 plus 1. So here the operation's addition. I was using powers before when I was thinking of a generic multiplication as the operation. Here it's addition. So I'm thinking of it as multiples now. So 4 is 1 plus 1 plus 1 plus 1, or 1 added to itself 4 times, or in other words, 4 times 1. What are the orders of all these elements? Well, 1, 2, 3, and 4 all have order 5. So that means that Z5, oh, it's getting away from me here, Z5 could be generated by 1, or we could also think of it as being generated by 2, or it's generated by 3, or it's generated by 4. In other words, that's what we wrote down here at the very bottom when we were talking about this topic before. But that's what we get, is that all the order of the elements are 5. Now, we did that by actually computing the orders when we were looking at the table. But now, with the results we have on subgroups, Lagrange's theorem, and the fundamental theorem of cyclic groups, we can get these results just through sheer counting. And so here's the way we look at it now, is we'd say Z5, oh, that's a cyclic group. Its generator is 1. What are the other generators? Well, it's a group of size 5. The other generators would be the numbers that are relatively prime to 5, so 1, 2, 3, and 4. Those multiples of the generator, 1 times the generator, 2 times the generator, 3 times the generator, and 4 times the generator. The generator is 1 in this case, so it would be 1, 2, 3, or 4 are all other generators of this group. Let's contrast this with Z sub 4. Z sub 4, get rid of this for now. Z sub 4 has these 4 elements. We've got a generator there. 1 generates it because every element in there is a multiple of 1. What are the other generators? The other generators are going to be the multiples of 1, where the multiple is relatively prime to 4. And that's either 1 or 3. So that's 1's a generator, 3 is also a generator. So this is generated by 1, it's also generated by 3. It's not generated by 2, because 2 does not have order 4. 2 only has order 2. 2 plus 2, or twice of 2, is 0. 2 has order 2 because it's already partially killed. You can think of it, it's just double 1. And it took 4 to kill 1. So if you double it, you've already sort of pushed it closer to the identity. So you just have to double it again to kill it off completely. So because 2 is 2 times 1, and that number there, the multiple, is not relatively prime to the order of the group, then it's already done some damage. And we're not going to get that to have full order of 4. So that's where this relative primeness comes in. Have you partially killed it? Have you partially pushed it towards the identity? If it's relatively prime, you haven't, so you still have full order, and so then it's still going to be a generator. Okay, so let's have a look at where we are now. We can take these results and we can write them in terms of our additive group, Z mod n, the group of integers mod n, and they basically, it was basically that last example we just did was Z4 and Z5, but we're just stating it more generally for Z sub n. And so what are the results we have? So we're in the group of integers under addition, mod n. K is a generator, so this is part A. K is a generator if and only if it's relatively prime to n. Part B says that for any divisor of n, you can find a unique subgroup that has that order, that size. So if n was 20, if we're looking at group of integers mod 20, because 10 divides 20, there must be a subgroup of size 10. And its generator is going to be given by the number 20 over 10, or 2. So 2 is the number that generates a subgroup of size 10 in that case. So that's what the second one says. We'll do some examples of this next. Part C is a little bit more cumbersome to write, but it's best to look back at it after we've done an example to see what it's actually saying. So here's our example. Determine all the subgroups of Z24. So what is Z24? This is all the numbers 0, 1, 2, all the way up to 23. So we got 24 numbers there. Addition is done, mod 24. So maybe the first thing we'll do is we'll look, what are the generators? What are the generators of Z24? Well, they are the numbers k such that the GCD of k and 24 is 1. They're precisely the numbers that are relatively prime to 24. So that would be 1, and then I just sort of think aloud when I do this. 1, that's relatively prime to 24. Yep, it's a keeper. 2, that's not relatively prime. 3 is not relatively prime. 4 is not relatively prime. 5 is. 6 is not. 7 is. 8 is not. 9 is not. 10 is not. 11 is. 12 is not. 13 is. 14 is not. 15 is not. 16 is not. 17 is. 18 is not. 19 is. 20 is not. 21 is not. 22 is not. 23 is. Okay. How do I know I didn't miss one? Well, there's a double check that we could do. The number that we need to get out, how many there are, is phi of 24. That's the number of numbers relatively prime to 24. We can look back in the appendix to see how to calculate phi of 24. Typically how we counted it before was we just listed them and then counted. But when the numbers get bigger, it's better to know how to work out phi of 24 without having to exhaustively count. So the way we do this is we factor 24. It's 2 cubed times 3. And the way the phi function works is it goes 1 prime at a time, and it drops the exponent by 1 and multiplies that by 1, the prime minus 1. So we drop the exponent by 1, multiply by the prime minus 1. Drop the exponent by 1, multiply by the prime minus 1. Let me see, I'm probably hiding it behind myself. I am, so I'll move that over a bit. There we go. And so that's going to be 4 times 2, which is 8. So we expect to get 8 numbers there, and we did. 1, 5, 7, 11, 13, 17, 19, 23. So we got all of them. So there's all the numbers that generate Z sub 24. So in other words, what we have is that the group generated by 1, which is all of Z sub 24, which consists of 0, 1, 2, 3, 4, 5, dot, 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 all the way up to 22, 23. That's our subgroup of Z24. It's the whole thing, so it's just itself. That has order 24. What are the generators? So I'm going to indicate these, maybe in pink. So 1 generates it. That means I can use 1, and just by repeatedly applying, the only thing I can do in a group is just the operation between 2 objects. Here I'm only going to start with 1, and I'm just going to operate on that object and itself. So 1 plus 1, that gives me 2. 1 plus 1 plus 1, that gives me 3. And I keep doing this, adding 1 to itself as many times as I can. I get all of those numbers. So that's what it means to be a generator. So 1 is a generator. Oops, I wanted that in green. What if I did that with another number? What other numbers would give me the whole list? Well, if I started with 2, and I did 2, 2 plus 2, 2 plus 2 plus 2, what I would get is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 0. And then back to 2 again. So I miss all the odd numbers. So 2 is not a generator. 2 does not generate the whole list of these numbers. So 2 is not a generator. What if I did it with 3? Well, what I would get is 3, 6, 9, 12, 15, 18, 21, and back to 0 again. So I wouldn't get the whole list. I'd only get a section of the list. So 3 is not a generator. So which ones do I get the whole list for? That's precisely what we listed above. Only the numbers that are relatively prime to 24. So 1, 5, 7, 11, 13, 17, 19, 23. If I start with any one of those numbers, repeatedly add it to itself, I get all of the numbers in that list, 0 through 23. That's what it means to be a generator. Okay, so what's next then in our list? Well, we're looking for subgroups, all the possible subgroups. Well, we know that a subgroup has to have a size that divides the order of the group. The order of the group is 24. So there's one subgroup of size 24. The next Biggest divisor of 24 would be 12. Is there a subgroup of size 12? Well, that's what this result tells us. For part B, for each divisor of 24, the set 24 divided by k is the unique subgroup of order k. So if I want to find one of size 12, since 12, taking k to be 12, since 12 divides 24, it means that 24 divided by 12, or 2, generates the unique subgroup of size 12. So that's what we get from that part B. To get a subgroup of size 12, or order 12, I use the number 2. And that gives me all of the even ones. 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh, almost got it in there. Can I move this stuff over a bit? I'll slide it up and I'll move it over a bit. It's just more satisfying having it all on the same line. 22 and back to 0 again. So there's a subgroup of size 12. 2 is how I generated it. Is there another way to generate it? Absolutely there is. Now this is where we have to sort of think, how can I get another generator? Now it's not the numbers that are relatively prime to 12. Why is that? Well, because none of the numbers in my list are relatively prime to 12. But we have to think carefully about this result here, theorem 11.5.2. It says that if I know one generator, I can get all of the other ones by taking the power of that one generator to a number that's relatively prime to, in this case, relatively prime to 12. I'm not going to do a power here because that's assuming the operation's multiplication. Instead, we're doing an addition operation, so I'm looking at a scalar. So here the result would be, if G is a generator, then K times G is also a generator when K is relatively prime to 12. So that means my other generators are going to be, well, all the numbers that are relatively prime to 12, which is 1. So that times 2. I'll put these numbers that are relatively prime to 12 in pink. So 1 times 2. What else is relatively prime to 12? 2 is not, 3 is not, 4 is not, 5 is. So the 5 multiple of 2 is also a generator. What's another generator? 6 is not relatively prime to 12, 7 is. So the 7 multiple of 2 is another generator. 8 is not relatively prime, 9 is not, 10 is not, but 11 is. So the 11 multiple of 2 is also a generator. So in other words, my generators are 2, 10, 14, and 22. So it's precisely 2, 10, 14, and 22. Any one of those 4 numbers will generate that entire list. So if I went 10, 10 plus 10 is 20, 10 plus 20 is 30, which is mod 24, which is 6, plus another 10 is 16, plus another 10 is 2, 16 plus 10 is 26, mod 24 is 2, plus another 10 is 12, plus another 10 is 22, plus another 10 is 32 mod 24, which is 8. So you can see as I keep adding 10 to itself, I'm going to get all of these numbers. But if I did the same thing with 4, I don't get all these numbers. Or 6 or 8, I don't get all of these numbers. I get a smaller collection of numbers. I get a different subgroup. So that's what we're doing here, is we're listing a subgroup and then all the possible ways to generate all those elements in that subgroup. So what's the next biggest divisor of 24? So we got 12. The next way we can divide 24 is, well, we can divide it with 8. So 8's a factor of 24. How can we get a subgroup of size 8? Well, I need to use the element 24 divided by 8, or 3. Because if I add 3 to itself a bunch of times, I get to 0 by adding it to itself 8 times. So 3 has order 8, so it generates a group of size 8. Let's list it out. 0, 3, 6, 9, 12, 15, 18, 21, and back to 0. So there's our 8 elements. Now we have to figure out which ones are also generators. 3 generates it. Does 6? Well, no, because as soon as I add 6 to itself 4 times, I'm back to where I started from, because 4 times 6 is 0. So 6 wouldn't generate this one. What about 9? What about 12? Which ones are generators? Well, the generators are going to be the numbers that are relatively prime to 8, which is 1, 3, 5, and 7. Those multiples of the generator that I already have. And the generator I already have, the one I know, is 3. So those are my generators. 3, 9, 15, and 21. So maybe I'll circle those ones and these ones in this case. Those are my other generators. So 3, 9, 15, 21. So there's our unique subgroup of Z24 that has size 8, and those are the different ways we can generate that subgroup. We could use 3 to generate it, we could use 9, we could use 15, or we could use 21. The next highest or the next largest subgroup would be 6, because that's the next highest divisor of 24. How can we generate a group of size 6? We could use 4 to do that, and that would be 0, 4, 8, 12, 16, 20. There's our subgroup of size 6. Which ones are also generators? We used 4, but what are the other ones? We take the numbers relatively prime to 6, which are 1 and 5, and we look at those multiples of the current generator we have, which is 4. So that means we have 4 and 20. So those are the 2 possible generators for this group, this subgroup. What else do we have? Well, 4 is also a divisor of, I'll move that down a bit, is also a divisor of 24, so the next biggest subgroup could be 4. That would be generated by, oh, wrong number, 24 divided by 4, which is 6. So that's 0, 6, 12, 18. 6 is a generator. The other generator would be the number relatively prime to 4 times 6, or 3 times 6, which is 18. So our 2 generators are 6, and 18 is another different generator. And so maybe I should point out here at this stage, we could write this as generated by 18. And similarly over here, I could write this as generated by 20. And in the previous case, I could write this as generated by 9. Or I could write it as generated by 15. Or generated by 21. Right, we have all of those different ways to write that subgroup. Okay, so we've got those 2 generators for this subgroup of size 4. We can also get a subgroup of size 3. That one would be generated by 8, and that would be 0, 8, and 16. But 16 is also a generator of it. That one might be a little bit easier to see. We don't need to do this multiples thing. We just say we've got a subgroup of size 3. 8 generates it. What about 16? Well, 16 is just going to be the inverse of 8, so it would also generate it. Or you can think of it as 8 has order 3. 16 is also an element in a group of size 3. The order of 16 has to divide the size of the group. So the order of 16 has to divide 3. So it's either 1 or 3. Since it's not the identity, the order of 16 has to be 3. So there's a few ways we can start to reason now about why 16 is going to generate this subgroup based on order, and it all comes back to divisibility properties, essentially, of the integers. So the possible generators, we could use 8 or we could use 16. What about a subgroup of size 2? Well, that's the one generated by 12, and that would just be 0 and 12. And there's only one generator there, it's 12. Or we could have a subgroup of size 1, and that's just the subgroup generated by the identity. And so the generator there is 0. Now what we'll see if we look down this list here, so looking down this list, is that every number appears somewhere. The numbers appear precisely next to the subgroup that is the same size as the order of the element. So 15, for example, 15 is an order 8 element in the group. If I add it to itself 8 times, I get back to the identity. That's why 15 is sitting here in this list next to order 8, because it generates the subgroup of size 8. And so on. We do that for every element. So the element of order, the element 20, 20 has order 6. And so, because 6 is the smallest multiple of 20, that's going to give me 0 when I add it to itself that many times and reduce mod 24. And so that's why the 20 is sitting on that line next to the order 6 subgroup. Okay, so what we had there for getting those generators, let's just finish it up with this. That says, for example, this first line, 2 was our generator. So to find all the other generators for that same subgroup, I took the numbers relatively prime to 12, and I just took those multiples of 2. 1 times 2, 5 times 2, 7 times 2, and 11 times 2. That's what this last line of this theorem is saying. For each k, which divides n, the number of elements of order k, so in this case, let's say you're in a group of size 24, how many elements have order 12? Well, for k being 12 in this case, the elements of order 12 are precisely those multiples of one element of order 12 that you know. And the one element of order 12 in this case was the number 2, 24 divided by 12. And it's all those multiples of 2 where L is relatively prime to k, or where L is relatively prime to, in our example, 12. So it's a little bit cumbersome when you write it like this to try to extract what is this really saying. All of that is just saying exactly what we did here. That's the size of the subgroup 12. List all of the numbers that are relatively prime to it, and those are the multiples you take of your existing generator, and those give you your generators for that same subgroup, or in other words, they give you all of the other numbers that are also of order 12. All right, so I just wanted to make sure we got these examples out of the way. I'm certainly happy to talk about them on Friday. I just wanted to make sure you at least had a couple of days to process this because of the homework assignment that you're working currently on. So we can talk about more of this on Friday, and we'll see you then.